Here's an example of additive synthesis that proceeds from the design of an idea for a spectrogram. And I would like to design a frequency trajectory such that it starts at a reference frequency, that's my 0 octave, it moves up 2 octaves, and then it splits into 2 partials where one goes up an octave and the other one comes down an octave. And then in turn, each of these partials, or each of these 2 partials, is also divided in 2. So we'll have one go up now a half octave, and then another decreasing by half octave. Same thing up here. So now we've bifurcated into a total of 4 partials, and then I'll repeat that process. Let me just draw that one more time. Say an eighth of an octave. Excuse me, that would be a quarter octave at this point. There we go. Same idea again. So now we have a total of 8. And so on. The idea is that at each point we bifurcate each partial, and then the amount of octave change is divided in half. Let's listen to the result. Let's try that again. Alright, so we see that the spectrogram duplicates what the original design intent was. So that seems to be working out pretty good. Let me show you kind of the overall structure that's hiding under the front panel here. As you look over that, it has basically one main loop, and one thing I wanted to point out here is that we really need to start with an initial vector of silence, because when that gets added together with the results from the general purpose oscillator, the shortest vector dominates the size of the output calculation. So we need to make sure that we start with a vector of zeros, which is the entire length of the sound that we're trying to create. What I'm doing with the quick scale is ensuring that when I add all of my results together, that I get a value or audio signals that lie within the 0 to 1 range. Just for fun here, I'm going to reverse the array before playing it. That's my rendition of the famous THX sound at the beginning of some movies.